Hi statisticians, welcome to section 8.1. So in this entire chapter, we're actually gonna think about something that we've assumed for the entire course up until now. And maybe you've thought about this before, but maybe not. We've kind of glossed over it. In pretty much every other section in this course, you've been given a value for the population mean. You've been given mu. Now, this is sort of interesting because a lot of our discussions have been about how we have to depend on a sample. We don't maybe know a lot of the statistics about our population. So this might have raised red flags. Like, if there's all these things that we don't know, then how are we just given the population mean? And if that raises red flags to you now, or if it did before, it should. Most of the time you won't be given the population mean. I mean, if you don't know your entire population, or if you only have data for a sample, then how would you be given your entire population mean? Instead, what we've been using was the sample mean, which we call X bar. And so we're going to take that in chapter 8 and use it to estimate the population mean. We won't be given the population mean most of the time, but we'll use this X bar, our sample mean, to estimate the population mean. And so our goal in this, pretty much this entire chapter, is to estimate the population mean, and we're going to hopefully improve on that idea of just using the sample mean, which is what we've been using up until now. Now, this is going to be divided into 3 different sections. In the first section, the population standard deviation will also be given. So, again, population standard deviation. That might also raise some red flags. Like, if we don't know the population mean, how on earth are we going to know the population standard deviation? And so in section 8.2, we're going to come back and do this when we don't know the population standard deviation. So we'll sort of take this step by step. Okay, so our goal in this first section, as I said, is to estimate the population mean when we do know the population standard deviation. So that's where this is all going. Now, before we get to this, let's start with a couple warm-up problems. So use the table from section 7.3 to find a z-value or a z-score such that 99% of the area under the standard normal curve lies between negative z and positive z. This was actually one of your homework problems. And it's going to come up again in this section in a pretty important way. So let's start by drawing a picture. So here's what this is asking. Remember, on the standard normal curve, 0 is in the middle. This is why we like it so much. It kind of looks like a number line. So 0 is in the middle. Now, they want us to find some z value, who knows what it is, where 99% of the area under the curve is between this z value and its negative counterpart on the other side, negative z. So who knows what this is? Maybe it's 2, maybe it's 2.5, I don't know. But if I go between that number and its negative, we're looking for whatever that z value is such that 99% of the area under the curve lies between negative z and positive z. So a couple things to remember here. The table that we have gives left areas. Remember, that table always gives us left areas. That's what the z table does. So if there's some way that we can take this picture and translate it into a left area, then that's what we should do. And there's actually multiple ways to do it. So let me do both ways. Okay, the first way to do it is to say, well, if 99% of the curve is in this middle section, then that must leave 1%, 1% on the outside here and here. So 1% would sort of comprise these two tails. Now it has to be split evenly. So 1% and 1% really means that there's 0.5% on this left tail and there's another 0.5% on this right tail. And that's what would give us that total of 1%, and that together with 99% makes up the whole curve. Okay, so let's think about how we can take this and turn this picture into a left area problem. As I said, there's two different ways. One of the ways that you can do it is to say, well, from this negative z-score, this negative z, the left area is 0.5%, or in other words, the area is 0.0050. And if I look in my table, okay, 0.0050, I might not find this exact value in the table, but again, I just want to get as close to it as possible. So I'm looking in the negative 2.5s, and actually there's two that are very close. So I can look at negative 2.57 and also negative 2.58. And the corresponding areas for those are 0.0051 and 0.0049. Now, I'll kind of come back to this later, but we want to be as conservative as possible on these, so I'm going to choose the smaller value. This is just our convention on this one. So I'm going to say that negative 2.58 is our closest value to that to that 0.5% area. Now again, remember that's negative z. So basically what I'm saying here is negative z equals negative 2.58. Well, if negative z equals negative 2.58, then of course z equals 2.58. So there's one way to do it. Now let's think about another left area that I can get from this same picture. Another left area would be starting here and all of this to the left. All of this. Now let's think about what that area is. So first of all, from here over to negative z, remember that's 99%. All this is 99% plus this additional 0.5%. So in other words, the area, sorry, kind of bright yellow, would be 0.9950. 99.5% of the curve is to the left of this z value. Remember, only that remaining 0.5% is to the right. So 99.5% or 0.9950 to the left. Now, again, going to my table, and I'm going to just scroll through the middle of the table looking for something that's as close to 0.9950 as possible. And again, I'm in the situation where there are two values, one on either side. So 0.9949 goes with a z-score of 2.57. And 0.9951 goes with a z-score of 2.58. Okay, so I want to be as conservative as possible, and what I mean by that is, remember I was looking for this 99.5% area, and this is very, 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 very close, but it's actually not quite there. It's just a hair under that 0.9950, and I don't want to shave any of this off. I don't want to like skip out on any of the area, so I'm going to go with the larger value, just so that I make sure that for sure I do have an entire 0.9950 area. Even if I do have a little bit of extra, I'd rather have extra than not enough. So z equals 2.58, of course the same answer we got doing it the other way, but in either case you just translate this to a left area and then go back to your table. So with that in mind, actually what you should do with that in mind is pause the video now and see if you can try this one. I can start you with a picture if you want. It's the exact same problem, but this time from z to negative z, we want 95% of the area. So on that first one, it was 99%. Now we want 95% of the area in here. So pause the video now if you haven't, and see if you can find this z-score. So hopefully you've had a chance to try it. If there's 95% of the area between z and negative z, then that leaves 5% in each of these tails. No, sorry. It leaves 5% between the two tails together. Now, when I split that 5%, it's going to leave me 2.5% on the left side and 2.5% on the right side. So again, 5% must be on the outside of 95, and then I just split that 5% evenly between the two. So 2.5% and 2.5%. So now I just have to think about how can I turn this into a left area problem. Now I'm going to take the left area from here, and that just saves me from doing that little switcheroo with the negative later, but honestly they're both like almost equally as straightforward. So from this z-score, which is what I'm looking for, right? Find z. I'm trying to find this z. I'm going to figure out what is its left area. So I've got this 95%, and then I've got an additional 2.5%, which would make my total area 97.5%. That's the left area. And again, that additional 2.5 is left over on the right side, but I only want the left area. So translating this into a decimal, this would become 0.9750. And now I'm going to go to my table. So 0.9750, let's see, 0.9750, actually this one's pretty lucky. 0.9750 shows up exactly in my table under a z value of 1.96. So that's what this is. This z-score is 1.96, which makes negative z equal to negative 1.96. And between those two values, between 1.96 and negative 1.96, lies 95% of the standard curve, of the area under the standard curve. Okay, so that's going to come back in later, although actually we don't really have to do that too many more times, maybe any more times. Okay, so again, going back to our setup, in this entire chapter, we are estimating the mean. We are estimating the population mean mu. So in many real-world situations, we deal with a sample rather than the entire population, which is why we've been dealing with the sample mean x bar, or why maybe we can find the sample mean x bar, but it's not necessarily realistic that we would just have the population mean. We have had it in this class, but in a real-world statistics situation, you would not be given the population mean. Okay, so suppose we have a simple random sample of some size n, which is drawn from a total population of values. Also, suppose that the value of our population standard deviation is known. Now, in section 8.2, we're going to revisit this and say maybe that's not so realistic, but we'll start out with a friendly example here. Suppose that we know the population standard deviation. There are two possibilities here. If our original data set already has a normal distribution, then who cares about the sample size? Everything that we're going to do works. If X has any other distribution, so I don't know, maybe bimodal, or maybe like a whole lot of skew, or I don't know, something weird. If it has any other distribution that's not normal, or if we don't know the distribution or we're not sure that it's normal, then the sample size has to be greater than or equal to 30. We saw this in chapter 7, that 30 is sort of that cutoff value. And so again, if we don't know what the distribution is, or if it's not normal, then we have to have a sample size greater than or equal to 30. Now, just a note here, we won't really see this in this class, but if the distribution that you're dealing with is really, really bad, very skewed or definitely not mound shaped at all, then sometimes you have to have an even larger sample, like 50 or 100. But for us, 30 is the cutoff. We won't deal with anything that's too terrible. Okay, so again, we have been using the sample mean as an estimate for the population mean, and there's actually a name for this. It's called a point estimate of a population parameter, which just means that it's an estimate using a single number. So X bar would be the point estimate for our population mean. Now, when you're using an estimate, we can compute something called the margin of error, which is like how close is your estimate to the real thing. Now, it's very easy to compute the margin of error when you have both the sample mean and the population mean. If you have both of the values, then you can say, well, oh, I estimated that the mean was 4, but it's actually 5, so my margin of error is 1, or whatever. But the problem is, if we're using an estimate in the first place, it's probably because we don't know the population mean. So we usually don't know both of these values. What we'll use instead is something called confidence levels. So we're going to express a certain percent confidence that our answer is in the correct ballpark. Okay, turns out we were actually doing this in the warm-up without actually calling it a confidence level. So suppose we want to find some level of confidence. We express it usually as a decimal between 0 and 1, but it's really a percentage. So oftentimes we talk about the confidence of 0.90, so think like 90%, or 0.95, so think 95%, or 0.99, like 99%. In each case, we choose something called a critical value. And the critical values were what we were finding in the warm-up. So the critical value is that z-score where you have a certain percent of the area, like 95 or 99, between z and its counterpart negative z. So z and its reflection on the other side. We found two critical values in the warm-up. We found the critical value for that 95% of area, and what we actually do is denote this z and then a little subscript, so set it down, 0.95. This is the z-score that goes with 95% area, and we found that to be 1.96. And then similarly on number 1, we found that the z-score, the critical value for 99% area, was 2.58. So we found two of these critical values in the warm-up. So these are critical values. That percent area is between the critical value and its negative reflection, its reflection on the other side. So I kind of already gave this away. Find, the way that we read this is z sub 0.99. Or you can say the critical value for 99% confidence. The critical value for 99% confidence. So what it's really asking is find the z-score such that 99% of the area is between z and negative z. And we already did this in a warm-up. We found z sub 0.99 is 2.58. 2.58. So again, we'll revisit this real quick. We do use the more conservative value to make sure that we didn't short that area at all. Now, another kind of equally simple problem, because we already did it. Find the critical value for 95% confidence. So find that z-score where 95% of the area is between z and negative z. And we already did it. Z sub 0.95, this was warm-up problem number 2, is 1.96. So we did 2 of these really important critical values. It turns out, you will have to do this a little bit on your homework, but we'll keep using the same values over and over again. Like you'll see this one all the time, you'll see this one all the time. So since we've already computed them, you won't have to do these again. In fact, I'll put it here, and then also in your formula sheet, you have a table of these critical values. So grab your formula sheet now. You can pause the video if you need to. Okay, so hopefully you have your formula sheet in front of you. This is on, if you go to the table with your z-scores, so go to your z-table, and there's actually 2 pages of the z-table. So there's the first page where it has all your negative z values, and then the second page where it has all of your positive z values. And toward the bottom left of your second page, the one with your positive z values, you'll see this table. This table is given to you on that page. So it tells you along the left the level of confidence. We found 95% and 99% in the warm-up. It gives you your confidence levels, and then it gives you the corresponding critical value for z. So you won't have to do those computations again. You can just use that table. Okay, so now that we have those, remember that one of our goals, or one of the things we could do if we knew both the sample mean and the population mean, is to find the margin of error. We can find sort of how close these two are to each other, which would just be the absolute value of their difference. Now remember, one of the things that we saw in chapter 7 is that the sample mean itself is a random variable. And as long as n is greater than or equal to 30, it has an approximately normal distribution. This was something that we called the central limit theorem. Furthermore, we had the formulas for the mean and the standard deviation of that new distribution, of the sampling distribution. So, using those, we can convert, and we've already done this, this is not new, we can convert x bar into a z-score. So remember, the normal formula is just x minus mu over sigma, but now we're going to plug this, well, we're going to plug this formula for the mean in here, and we're going to plug this formula for the standard deviation in here, and we're plugging in the mean in here. So converting this into the language of the sample mean, we find that z equals x bar, there's our mean, minus, now we'll think, well, what is the mean of the sampling distribution? Turns out it doesn't change, so still just mu. What does change is the standard deviation. So instead of just sigma, now it's sigma over the square root of n. So if you're confused by the difference between these formulas, there is a real easy way to tell them apart. For the first one, you're just plugging in x. So the regular x formula doesn't change. It's x minus mu over sigma, same thing we've done before. The second one, with this sort of modified standard deviation, is only when you're plugging in a sample mean into it. So you only modify the denominator when you're using a sample mean instead of just a regular x value. And that'll be clear in the problems which one you're doing. So substituting that back into this formula, the formula on the previous page, this formula, where we have z is between our two critical values, the negative z value and the positive z value, equals that confidence level. So plugging that in here, don't worry too much about this, you won't have to recreate this part. Plugging this in here, where I saw a z, gives me that. And then I'm just going to do something a little bit funny, and you can just kind of take my word for it. Again, you won't have to recreate this at all, so you're just watching at this point. I'm going to take this inequality and multiply all sides of it by the denominator. Basically what I want to do is clear the denominator in the middle of this inequality. So I'm going to multiply the left side of the inequality by sigma over square root of n, multiply that here. I'll multiply the middle of the inequality by sigma over square root of n, and I'll multiply the right side of the inequality by sigma over square root of n. And what that gives me, well, this sigma over square root of n cancels this sigma over square root of n. And so really what that gives me at this point is a little bit of technical detail here. Whoops. X bar minus mu, and I'm putting in an absolute values because I'm kind of changing the format just a little bit, but don't worry about it. Is less than, and so the right side becomes z sub c, whatever that critical value is. And remember, the critical values are given in this list. These are the critical values that you're going to use, so you'll have a number to plug in for this, times sigma over square root of n, this critical value times sigma over square root of n, and the left side kind of becomes the same thing, these two multiplied together. So negative z sub c times sigma over square root of n. Okay, so here's what this tells us. You do not have to memorize this formula. Here's what this tells us. It tells us that the error, basically like the difference between our sample mean and our population mean, has to be somewhere, well, less than this value. Less than this value. I really didn't need the absolute value there. Our error between these, the distance between these, must be less than this value. And so we're just going to name this the error. And I've gotten a little bit ahead of myself because this is actually all laid out on the next page. Here is that formula. And this is given to you in your notes. So again, you don't have to recreate any of that stuff that I just did. Here's the formula that you have in your notes. I'm just explaining to you where it comes from. Okay, so putting this together with the statement that we'll use from probability becomes this. And really the important part that you need to know is this part. This is called a confidence interval for the mean. Now, let me just double check. I'm looking in chapter 8 on your note, on your formula packet, and yeah, sure enough, this here is the first formula on there. This is the first formula on your formula packet under chapter 8, and this is the second formula on your formula packet for chapter 8. So all of this is given to you, and honestly what you really need is just to be able to plug in numbers into these formulas. Okay, so let's put this in the context of an example. Actually, let me just make one other really important note here. You're going to be plugging something in when you're making a confidence interval. The problem is going to say, give a confidence interval for mu. So when someone asks you for a confidence interval, you will plug something in for x bar, you will plug something in for E, you will plug something in for this X bar, and you will plug something in for E. The thing that I want to point out is that mu stays mu. You don't plug in a number here. You do not plug in a number for mu. Mu stays mu, and that's going to be part of our answer. Okay, I think doing an example will clarify what I'm talking about. This is actually a really easy process, but I think probably up until now it might sound a little bit intimidating, but this is not bad at all. Okay, so example, Casey usually jogs 2 miles per day. The standard deviation of her times is sigma equals 1.80 minutes. So again, given standard deviation here. During the past year, Casey has recorded her times to run 2 miles. She has a random sample of 90 of these times. So there's our sample size. We've got 90 data values, so n equals 90. For these 90 times, the sample mean was 15.60 minutes. Let mu be the mean jogging time for the entire distribution of Casey's 2-mile running times. Find a 0.95 confidence interval for mu. Okay, find a 0.95 confidence interval for mu. This tells us we want our confidence level to be 0.95. This is our confidence. Okay, our answer is going to look like this. I'm following this formula. You can look at it here or in your Chapter 8 formula packet. This is a confidence interval. So our answer is going to look like x bar minus the error, E stands for error, is less than mu is less than x bar plus the error. Okay, we're going to plug something in here for x bar. We're going to plug something in here for E. We'll get it in a second. Mu stays mu. You never plug in anything for mu. Mu stays mu. We'll plug something in here for x bar, and we'll plug something in here for the error. So let's see. Well, the first part is actually pretty easy. I mean, x bar is given to us in the problem, so we can say 15.60 minus, and then I need the error, is less than mu, is less than 15.60 plus the error. So now I need to find the error. Basically, I'm just stuck finding this value. That's all that's left for me to do. And again, mu stays mu. So I'll use that other formula on the previous page. It's the other formula in the Chapter 8 formula packet that we have so far. The formula for E. So this says E equals Z sub C times sigma over the square root of n. Okay, well, we know from the problem it said that we want our confidence to be 95%. So we're looking for Z sub 0.95. So we'll start with that, and then let's see, sigma, well, that's also given to us in the problem. So 1.80 over the square root of n, and n was given to us in the problem, n is 90. So really the last thing we need to think about is what is this Z sub 0.95, that 95% critical value? Well, lucky for us, there's a table. There's a table right here. So I'll look at that 0.95 or 95% confidence, and there's my Z sub C. There's my critical value, 1.96. So 1.96, everywhere you see that Z sub 0.95 times 1.80 over the square root of 90. Okay, so throw that into your calculator and let's round it to 2 decimal places. Okay, so when I throw that into my calculator, I get 0.37188, and so I'm saying we're going to round to 2 decimal places, so I'm going to stop right here. oops, 0.37, approximately 0.37. Okay, so coming back to my answer format, everywhere I see an E, I'm going to put 0.37. Everywhere I see an E, I'm going to put 0.37. And now this is it. This is pretty much going to be my answer. The only last thing that I need to do is just combine this. So 15.60 minus 0.37. So when I put that into my calculator, I get 15.23 is less than mu is less than, and again on this side, add those together, 15.97. So this is a 95% confidence interval. Now, it's called an interval because I have two different values that basically give me a lower bound and an upper bound for my population mean. So here's what this means. It means that Casey jogs 2 miles a day. She has not recorded her time for every single one of these runs. Maybe there's hundreds of data values, I don't know. But what she does have is data for a sample of size 90. She's recorded times for 90 of the runs. So she's got a sample mean, 15.60 minutes, and she's also got a standard deviation, which is 1.80. Now, using these two values, we can say with 95% confidence that the mean of all of her runs, the entire population of data, is somewhere between 15.23 and 15.97 minutes. If we were able to average the times for all of her runs, we're 95% sure that it will be somewhere between 15.23 and 15.97 minutes. So just a little note here. All we can say is that we're 95% confident here. All we can say is that we're a certain percent confident that the interval actually contains mu. We can never say for sure that the population mean is between these two numbers. I can say with 95% confidence, but I can never say with 100% certainty. Now, if you want your confidence level to be higher, we can go all the way up to 0.99. And you would use a different z-score. But there are ways to increase confidence. You can basically go all the way down to 70%. You're like, sort of confident. Or 99% confident, like pretty confident that we're at least in the right ballpark. Okay. So one last thing here in this section. Note that in all of the previous examples, well, I guess all there was one. Note that in the previous example, we were given the sample size. So we were given n, and then we found E, the margin of error. We found the error, we were given the sample size. Well, sometimes you want to go backwards from that. So sometimes, especially when you're doing something like maybe giving surveys or something like that, you start by setting the maximum error that you're willing to tolerate. So maybe you say, look, I want to give out as many surveys as I have to make sure that my error is either 3% or smaller. Like I'll tolerate 3% error, but nothing larger than that. So how many surveys do I have to give out? So oftentimes you set your maximal margin of error and then you decide on your sample size, n. So in the last example, we were given n and then we found E, but there's actually another way that we can sort of go backwards from this. We can start with E, the error, and then we can find n. And to do that, we use this formula, which is just a sort of like a rearrangement of a formula that we already used. And again, this is in your formula packet in the Chapter 8 section. So we'll plug in our critical value, we'll plug in our standard deviation, we'll plug in the error that we're willing to tolerate, and then we'll take that entire quantity and square it. A note here, if n is not a whole number, you'll increase n to the next higher whole number, because n is a sample size. So if I get like, say, 15.2, well, it doesn't make sense to say just give out 15.2 surveys. So I'll always bump that up to the next higher whole number, even if it would round down like 15.2. I'm not going to round it down to 15. I'm always going to bump it up to the next highest number. Okay, so an example of that. A wildlife study is designed to find the mean weight of salmon caught by an Alaska fishing company. A preliminary study of a random sample of 50 salmon showed that the sample standard deviation equals 2.15 pounds. And actually, let's change this for right now, because this is what we're going to do in section 8.2. Let's call that sigma for right now. So our standard deviation is 2.15 pounds. How large a sample should be taken to be 99% confident, there's our C, 99% confident that the sample mean is within 0.2 pounds of the true mean weight? There is the error that we're willing to tolerate. I want our real answer to be within 0.2 pounds of the true weight. Okay, oh, and it says it here. Assume S is a good approximation for sigma. So we'll just pretend that S and sigma are pretty much the same thing. So I'll take those values and I will plug them into this N formula. So it says N equals, now, Z sub C. In our case, we know that we want our confidence level to be 0.99. So I'll have to find that in just a second. It's going to be times sigma over E and this entire thing squared. So let's go back to our table, 2 pages back, and find our critical value for that 99% confidence. So 2.58. So everywhere I see Z sub 0.99, that's going to be 2.58. So I'll plug that in here. 2.58 times sigma, which we're saying is 2.15, over E. The error that we're willing to tolerate is 0.20 pounds. And we'll take that entire quantity and square it. Okay, so I'm going to plug that into my calculator. Now, careful with your parentheses here. Make sure that you're entering it exactly as it shows up on the page. Squared. Okay, so I find 769.230225. Okay, this would round down to 769, but remember, we always bump this up to the next higher whole number. So I'm going to say my answer is 770. So this is basically saying how many salmon do we need to measure to be 99% confident in our sample mean? And the answer is 770 salmon. 770 will get us to that within 0.2. Okay, so pause the video now and try the I really understand this section, and we'll go over it in just a moment. So hopefully you've had a chance to try these two problems, but I'll go over them both. The first one says, Kyle likes to jog 3 miles. From experience, he knows that sigma equals 2.40. So this is his population standard deviation for his jogging times. For a random sample of 90 jogging sessions, there's N, the mean time was X bar equals 22.50 minutes. Let mu be the mean jogging time for the entire distribution of Kyle's 3-mile running time over the past several years. Find a 99% confidence interval for mu. Okay, so we want our confidence level to be 0.99 or 99%. And using that, I'm just going to start writing out the format of my answer. So my answer is going to look like x bar minus e is less than mu is less than x bar plus e. Now remember, you're going to plug in values here for everything except mu. Mu stays mu. Mu is going to stay mu in all of our answers. So some of these things are easier than others, like x bar, well, that's just given to us in the problem, 22.50. No work required for that one. On this side also 22.50. There's x bar, so that's done. But we do have to do a little bit of work to get the error, E. Now, thankfully, there's a formula for this. It's not too bad. E equals Z sub, well, in this case, 0.99 times sigma over the square root of n. Now, from my table, I know that the 99% critical value is 2.58 times sigma. Sigma is 2.40. And the square root of n, so n is 90. When I throw this into my calculator, square root of 90, I get, I'm going to round to 2 decimal places here, 0.65, approximately 0.65. It's actually 6526941, but I'm going to round it to 0.65. So that's going to go in here everywhere I see this E value. And then I just need to simplify the left and the right side. So one more time, mu stays mu. Do not plug in anything for mu. Mu stays mu. So when I subtract 22.50 minus 0.65, I get 21.85. Mu stays mu. And when I add these two, 22.50 plus 0.65, I get 23.15. There's my 99% confidence interval. So I have no idea if mu is for sure somewhere between 21.85 and 23.15. All I can say is that I'm 99% confident that it's somewhere between these two values. Doesn't mean it's exactly halfway. It might be 21.86. I don't know, but I'm 99% confident that somewhere between 21.85 and 23.15 lies the actual population mean for Kyle's running times. Okay, one more. Suppose X has a mound-shaped distribution. When you read this phrase, this translates to you as normal, with sigma equals 3. Find the minimal sample size required, so find n, so that for a 95% confidence interval, the maximal margin of error is E equals 0.4. Okay, so I'm going to use my formula for n, which was Z sub C. Actually, I'm going to go ahead and plug in this 0.95. So I'll say 0.95 here times sigma over E, and that entire thing squared. Now, my 95% critical value from the table is 1.96. Sigma from the problem is 3. E from the problem is 0.4. And I'm going to square this. So 1.96 times 3 divided by 0.4. And square that whole thing, I find 216.09, which would definitely round down to 216. But again, we're not rounding. We're going to increase this to the next highest number. So 217. 217 is the sample size if I want to be 95% confident in my answer. Okay, so next time, in the next section, we're basically going to revisit the exact same stuff. We're going to do the whole process over again, except we're going to change this part. So in section 8.2, it's going to look like that when sigma is not known. And it's really not going to be too bad. We'll just estimate this using our sample standard deviation, but we have to pay for that in a certain way because it's just not going to be quite as good as if we know the population standard deviation. But honestly, pretty much the same process in section 8.2 with just a couple little tweaks. So I'll see you then.